For decades, neuroscientists studying appetite and reward have relied on a surprisingly narrow model for eating: liquid diets. The reason is purely practical. Liquids are easy to deliver and perfectly measured by simple lactometers. But drinking isn't eating. Consuming solid food introduces an entirely different set of complex motor actions, demanding precise jaw coordination for biting and the sustained rhythmic force of mastication. This process generates what we call mouthfeel. It's a continuous, dynamic stream of trigeminal touch and gustatory taste signals. A liquid diet provides a predictable sensory loop, but solid food creates a chaotic mechanical feedback system that the brain must constantly monitor to regulate bite size and eating rate. Current smart cages attempt to track this solid food intake using automated weighing scales. These systems measure the total grams consumed over minutes or hours, but they entirely lack the millisecond temporal resolution required to sync up with fast-firing neural recordings. Trying to solve this with purely video-based AI tracking introduces new hurdles. These visual models demand massive computational power, and they frequently generate false positives, recording a mouse simply standing near a food hopper as actively eating. To accurately map the brain's appetite circuits, the field requires a completely different approach. Researchers need an instrument capable of capturing the messy physical reality of chewing at the exact temporal speed of an electrophysiological recording. Enter the Crunchometer. This low-cost acoustic system monitors solid food consumption down to the exact millisecond. Instead of expensive scales, the straightforward design positions a basic condenser microphone adjacent to the food pellets on the testing box. The use in audio creates an immediate engineering challenge. A busy laboratory is filled with ambient hums, footsteps, and ventilation systems. The system has to isolate the minuscule, rapid sound of a mouse eating from all of that background interference. The solution lies in targeted signal processing. First, the audio undergoes a strict bandpass filter, designed to carve out everything except the specific high-frequency acoustic signatures generated by a physical crunch. Engineers pinpointed the exact feeding profile using raw spectrograms. A mouse biting a solid pellet consistently registers within a 500 to 950 Hz band. The software then applies a strict threshold to this isolated spectrum, dropping all audio failing to break -85 decibels. While many audio systems use a dynamic rolling threshold like a Z-score, this fixed decibel limit serves a specific biological purpose. It flawlessly captures states of absolute silence, correctly logging exactly when a satiated mouse stops biting entirely. Through this acoustic pipeline, the complex act of mastication is distilled into a clean, high-resolution data stream, stripped of noise and ready for behavioral analysis. With the audio isolated, the system moves to binarization. Any 1-second block of sound that crosses that -85 decibel threshold is tagged with a 1, logging it as a putative bite. Microphones capture sharp pellet fractures, but miss softer chewing, leaving fragmented spikes. To fix this, the software applies a temporal rule. Bites separated by less than 5 seconds are fused into a single continuous feeding bout. Conversely, if silence lasts more than 5 seconds, the system logs a definitive end to that bout and resets for the next feeding event. This time interval clustering corrects for the microphone's physical limitations. It ensures researchers are capturing the total physiological duration of the mastication process, filling in the quiet gaps between the sharpest crunches. But acoustics alone leave a critical blind spot. A microphone can record a physical bite, but it cannot determine whether the mouse is eating standard chow or a high-fat diet. Mice routinely engage in non-feeding behaviors that confuse audio sensors. They aggressively gnaw on rigid plastic cage components, producing crunches indistinguishable from actual eating. To solve this, the Crunchometer introduces a second modality: lightweight spatial video classification using defined regions of interest. A bottom camera calculates motion energy within specific zones drawn directly underneath the food pellets. If an acoustic bite triggers while motion spikes inside a food zone, it's classified as consumption. Otherwise, it's rejected as an artifact. By relying on simple audio frequencies to determine exactly when a behavior occurs and basic spatial zones to figure out what is being chewed, this setup completely bypasses the computationally heavy lag of AI video tracking. To validate a new measurement tool, its output must be tested against the historical gold standard of behavioral neuroscience, manual human observation. When tested head-to-head, manual annotation revealed a severe temporal lag. On average, human observers misidentified the start of a feeding bout by over 8 seconds and routinely logged the end of a bout more than 10 seconds late. This failure comes down to logistics. Human annotators are constrained by baseline reaction limits, mental fatigue across hours of video review, and the sheer visual ambiguity of trying to spot tiny rodent chewing motions on a monitor. The Crunchometer's automated logic removes dat subjectivity, yielding rigid, mathematically reproducible timestamps for every single feeding interaction, and the biological accuracy holds up. The total bout counts generated by the algorithm correlate strongly with the physical weight in grams of the food the mice actually consumed. The final output of this pipeline is a synchronized, high-resolution ethogram. It's a color-coded map charting exactly when a subject was eating, what diet it chose, and for how long. This level of split-second precision is an absolute necessity. Without it, researchers simply cannot map physical feeding behaviors to the incredibly fast, dense data streams produced by high-speed neural sensors and in vivo electrophysiology. By democratizing the acoustic analysis of solid food, the Crunchometer finally provides neuroscientists with the exact structural timestamps required to decode the neural circuits governing appetite and satiety.